Okay, so now we have under our belts knowledge and tests about the mean of a population and of two or more populations when we have normal data. In other words, when dealing with continuous measures. Now, let us switch attention to the situation when we have count data. Let us start with the binomial situation. Now, what we have already seen about the binomial model is that it is useful for modeling dichotomous data. Yes, no, male, female, alive, dead, etc. Now, our challenge is to estimate P. Our challenge is to estimate P in the binomial distribution. We usually assume that N is known, but now we're going to estimate P. So P, remember, is the probability of success. We're going to repeat an experiment N times, and P is the probability of success. So for example, we might think of a village, and we might think of 40 people in the village. And P is the prevalence of vaccination. So we decide whether a person is vaccinated or not, a child, let's say, is vaccinated or not. And that we're going to model as a binomial. We remember we had that the mean of such a situation was NP, and the standard deviation was the square root of NP1 minus P, if we are interested in the total number of successes. So of those 40 people, how many are vaccinated? So, in the usual spirit of hypothesis testing, we approach inference about P by saying, if this is the truth, what do I expect to see? Okay, so it's our usual approach, and what we can do is go to the Quincunx. So here is the Quincunx, and what I did was I set it off with P is equal to 0.5, and here it is with 14 rows. So that's like asking 14, going to a village and looking at 14 kids to see if they vaccinated or not. And this is P is equal to 0.5, that we will go either left or right every time the ball bounces. So either left or right with equal probability. We are going to look at this very special situation when we only have one observation. So here we go. If P is equal to 0.5, we expect the observation to come down the center, and roughly, well, actually this is exactly in the center, but I just let it go once, and this is where it ended up. Whereas if I change the left probability to 0.8, then you'd expect it to end up somewhere down here, and in fact here it is. When I let one go, it arrived there. When I change the left probability to 0.3, then you'd expect it to end up at this end, and there it is. And lastly, if I said 0.1, then it should be even more to this end, and there it is. All right, so here is the challenge. The challenge is I'm going to tell you one, where one has landed, and you or we have to determine what this is. Okay, so think about this. We don't know what this is. All I'm going to tell you is where the ball landed after 14 rows. So there's 14 rows. Okay, that's the 14. And knowing where the ball landed will allow us to make some inference about this P. Okay, so for example, here are the 4 that we've just looked at. When the left probability is 0.8, it landed there. When the left probability is 0.5, it landed here. When the left probability is 0.3, it landed there. When it's 0.1, it landed here. Now, it's not going to land in exactly the same spot every time. That's for sure. But if we do this repeatedly, we might get a picture like this, if we do this over and over and over and over again. actually these are not from the Quincunx. These are all with n equals 14, but this one is with p equals 0.2, this one with p equals 0.5, 0.7, and 0.9. So that is why we expect the ball to be somewhere here. It can go all the way up to here, but we typically expect it to be down here. We typically expect it to be in the middle when p equals 0.5. We typically expect it to be a little bit to the right when p is 0.7. When p is 0.9, we expect it to be quite a ways over to the right. Now, if we increase this number, if we increase the number n equals 14, then what we see, here it is with n equals 30, what we see is a tighter bunching up of around the mean, if you will. And so, just like with the flab rats, it's much easier to distinguish between these two, for example. It's much easier to distinguish between these two. And if I put them in different rotation, you'll see that it's true when I do this versus that, etc. So it looks like it's easier with n equals 30 to make a distinction. Now, with n equals, let me increase the n even more to n equals 75. Now they really are separated, those two, and this one also, they really are separated. So it's much easier to distinguish between these p's when my sample size is bigger. But you say to me, oh no, look at this, the scale is different. Here you're going up to 80. Sure, it should only be up to 75, so it should only be up to here. So, but here you're going up to 75. So the scale is different here, whereas here it was 30, and back here it was 15. So this is 15, should only be 14, of course. But I'm just talking about the scale now. So there it is, 30, and here it is 80. That is why we are seeing this, you might say. All right, let me fix that by dividing by the maximum value x can take. So let's divide by that, and let's go back to n equals 14, and now when I'm dividing by n, the maximum value it can take is 1. So here it is the same scale. So it's not a question of scale, it's just that this is getting closer and closer. But now when I do this, when I divide by n, so what I'm doing is I'm dividing x by n. Then what I'm looking at is the proportion. So x is the total number of successes, divide that by the total number of trials, then we've got the proportion. So as our estimator of p, we can look at the number of successes and then divide by n. Okay, so if d is equal to 0 or 1, remember that was the at every trial, what happens? Then our estimator of p can be the total number of successes divided by the total number of trials. Why are we doing this? Because, oh, look at that. That means that our estimator of p, which is what we've been trying to get at, is just the mean of the d's. So this is d bar. So we can appeal to the central limit theorem to help us out. So finally we have an estimator of p, which is just the average of what happens at every single trial.